Hi, I'm Wolf Honoré, and today I'll be talking about the ADO model, which is a new fault-aware model for compositional verification of strongly consistent distributed systems. This is joint work with Jung Kim, Jiyoung Shin, and Zhong Shao. Most distributed applications rely on a class of distributed protocols that guarantee strong consistency in order to reliably store critical data. This includes Paxos and Raft, which are notoriously complex, so we'd like to use formal verification to ensure that everything behaves correctly. Take, for example, a distributed key-value store. Under the hood, it might be implemented by a cluster of servers running multi-Paxos, but we'd like to use a proof assistant like Hawk to prove that it behaves as we'd expect according to a typical abstract specification. To do this, we need a model in which to write the specification. Let's see what the existing options are and what challenges each poses. One very natural choice is to mirror the implementation and represent it as a set of servers communicating over a network. This is the approach taken by several verification frameworks, including Diesel and Anaris, and it has the advantage of making it easier to prove a refinement with an implementation or even extract an implementation from the specification. The problem is that it forces us to consider three types of issues at once. First, there's the network model itself, where lots of things can go wrong. Servers can crash, messages can interleave, and packets can be dropped, duplicated, or delayed. These are problems that a protocol like Paxos needs to be aware of, but ideally the application shouldn't be concerned with them. Second, we have the distributed protocol. Its job is to handle network failures and manage concurrency to keep the servers in sync. This involves subtle linearizability arguments involving multiple phases, quorums, and timestamps that again are not directly relevant to the application. Lastly, there's the application logic for the key-value store, which is what we're mainly interested in. Handling all of these concerns at once quickly becomes impractical, so what we'd like is for an abstraction to disentangle them and let us pretend that the key-value store is just a regular object. This is essentially what state machine replication, or SMR, does. In this model, the system is treated as an object that keeps a log of all the methods that have been applied. It hides the internal network and protocol communication details inside a black box remote procedure call interface. Verification frameworks like Ironfleet and Verdi allow developers to write applications and reason about them at this level, which is clearly much simpler than the network level. The problem is, for some cases, this is actually too abstract. That's because distributed systems are fundamentally different from regular objects in a few key ways. One of these is partial failure, which is when an operation doesn't succeed at the time it was called, but still has an effect on the system going forward. Here we have our same distributed key-value store with three servers, each of which maintains a local set of mappings. In order to maintain consistency between the servers, a majority of them must agree on a particular mapping before it is considered committed. Committed mappings are guaranteed to be persistent and observed by clients in the same order, but this is not true for uncommitted mappings. Suppose Alice tries to map foo to bar, but due to network problems, only S1 receives the message. Eventually, the request times out, which means that it fails in the sense that the mapping was not committed. Later, Bob reads the current state of each server and sees that S1 has a mapping that the other two are missing. To help bring the servers back into agreement, Bob tries again to map foo to bar, and this time he succeeds. This is why Alice's request was only a partial failure. Although it was uncommitted, it left a visible effect for Bob to observe that resulted in it eventually being committed. This kind of behavior is completely hidden by SMR, usually by simply retrying the failed operation until it's committed. However, we claim that for some situations this is insufficient and that partial failures should be exposed by the model. We're not the first to make this observation. Jim Waldo wrote that partial failure is a central reality of distributed computing, and that being robust in the face of partial failure requires some expression at the interface level. Partial failures subtly interact with every aspect of a protocol, from core features like leader election to important extensions such as reconfiguration. In order to fully understand and handle these relations, a model needs to accurately represent partial failures. Certain applications can also exploit them for performance gains. Tapir and Speculator are systems that, thanks to application-specific knowledge, are sometimes able to proceed without waiting for a command to fully commit. Because these rely directly on partial failures, they would be impossible to verify using SMR. If SMR is too abstract, the network-based models have the opposite problem. They clearly expose partial failures because they expose almost everything from the implementation. However, as I mentioned, it's hard to do anything too involved with them because there's no clear separation between application and protocol logic. Since neither of these models, and by extension the verification frameworks that use them, is well suited to handling partial failures, our question is, can we design a new model that finds the sweet spot between them? This is where the Atomic Distributed Object, or ADO model, comes in. This is a new abstraction for distributed systems that is detailed enough to be fault-aware, by which I mean it exposes partial failures to the application, but still has a clean separation with most protocol-specific details. ADOs are also compositional, meaning objects can be built and verified separately, but then put together to form larger applications. This is all great on paper, but to actually test this model, we built an end-to-end verification framework around it in the Coq Proof Assistant, which we call ADVERT, for Atomic Distributed Object Verification Toolchain. Using ADVERT, we were able to verify several non-trivial composition case studies, including a lock-free key value store and a version of two-phase commit with replicated resource managers. To show that the ADO model faithfully describes actual distributed behaviors, we proved that some common network-based protocols refine the ADO model, including several variants of Paxos as well as chain replication. We also went a step further and used certified concurrent abstraction layers to prove that a C implementation of multi-Paxos refines its network-based specification, giving an end-to-end connection from an abstract ADO all the way down to an executable implementation. Unfortunately, I don't have time to cover all of these today, so the rest of the talk will focus mainly on these highlighted points, but I encourage you to check out the paper for more details. In some ways, the ADO model is similar to state machine replication. It treats a distributed system as an object with application-specific methods. Like SMR, there is a log of committed methods that also contains the logical timestamp of when each method was called, which is important for assigning a consistent global order to concurrently called methods. One key difference with SMR is that instead of hiding uncommitted methods, they are explicitly modeled in a tree structure. We call it the cache tree by analogy with shared memory systems where committed methods are like persistent memory and uncommitted ones are like volatile caches, which can either be flushed to the persistent log or overwritten. In addition to invoking methods, there are two additional operations called pull and push, which help maintain consistency under concurrent conditions. These model abstract versions of similar operations in multi-Paxos, RAF, and chain replication. For example, multi-Paxos has two phases, prepare and commit, with local updates in between, which map to the ADO operations like so. To help visualize this relation, I'll walk through an example with corresponding ADO and multi-Paxos states side by side. On the multi-Paxos side, we have three servers, each with a log of methods and logical timestamps. Every server also tracks the largest timestamp it's seen, shown to the left of the figure. The goal is for one of the servers to act as a leader and replicate its log entries to at least a majority of the servers, including itself. In this case, S2 is currently the leader, but S1 decides to start a new election for itself. It first increases its timestamp to 5 to indicate the start of a new round or term. I'll use a dotted outline in the figure to indicate the changes on each step. It then broadcasts a prepare request, and if the servers have not already voted for a candidate with a larger timestamp, they update their own timestamps. The servers acknowledge the candidate's request with a snapshot of their logs. If the candidate receives votes from a majority, then it becomes the leader and selects the most up-to-date snapshot by comparing the timestamps of the latest entries. In this case, that's S2's log because its last entry has timestamp 4. Now, on the ADO side, pull accomplishes a similar goal, except we no longer see the individual servers. Each entry in the cache tree represents a method in some server's log that a candidate might observe, so the caller is assigned one of them arbitrarily. Like for multi-Paxos, the chosen cache here is XYZ maps to 123, as indicated by the dotted outline. You can think of pull as acquiring a preemptible lock on a snapshot of the object. The lock must be acquired before updating the state, but it can be taken away at any time by another leader. It's also possible for prepare or pull to fail if not enough servers vote. Returning to multi-Paxos, once S1 has been elected leader, it can append new methods to its log using its new timestamp. It can continue this as long as it wants, with every method using the same timestamp to indicate that they were all called during the same round. Likewise, in the ADO model, a caller can invoke arbitrarily many methods, with new caches being added onto the branch that it was assigned by pull. To commit its methods, S1 first sends XYZ maps to 123 to bring S3 up to date, overwriting the uncommitted entry that it had before. Next is B maps to G, and as long as the servers haven't voted for a new leader in the meantime, these methods are now committed because they're in a majority of the logs. Finally, S1 sends bad maps to cow, but this time the network drops the messages. This is an example again of a partial failure because the method is uncommitted, but it's still in S1's log, so it could be committed later. In the ADO model, push commits cache tree entries by adding them to the persistent log. In order to model partial failures, it may only commit some prefix of the new methods, which in this case is just the first two. Then, as with S3's old uncommitted entries, the sibling branches represent stale log entries that should no longer be observable, so they're pruned from the tree. Any partial failures remain in the tree because they could still be committed in the future. As you can see, the ADO model hides low-level details like network failures and quorum sizes, but still captures high-level features like the safety guarantees about committed methods and the existence of partial failures. Now I'll show some examples of working with ADOs and combining them into larger distributed applications, or DApps. Let's take the same key value store example again, but say that instead of storing just the key value mapping, we also want to keep some metadata about the value, such as its length. We could implement this as an ADO with a replicated array to store both the data and metadata, but suppose instead that we decide to store them on separate clusters of servers to increase their reliability or availability. In that case, we need two ADOs, one for the data and one for the metadata, as well as some way of keeping them in sync like a lock. Then, to tie everything together, we define a DApp called kvlock with the procedure set, which is going to communicate first with the lock object to acquire it, then send the value to the first distributed vector object, then send the metadata to the second vector object, and finally release the lock. Get and getMeta work similarly. The first thing set has to do is call pull on lock, but remember that pull can fail, so we have to decide how to handle that. One option is just to retry it, like so. Next, it invokes the tryAcquire method, which fails if the lock is already held. Then, to make sure that the result is fully committed, it repeatedly calls push. Finally, if the lock was not acquired, then it aborts. Notice that everything so far is just to call one method, but we have already seen several possible failures that we can handle in a variety of ways. For example, kvlock could abort instead of retrying. Or it could set an upper bound on the number of retries. With just these three operations, pull, invoke, and push, developers have much more flexibility than with SMR to define failure recovery strategies. Of course, sometimes you may just want the error handling to be taken care of internally. This can also be easily done with a simple method call wrapper that retries pull and push as needed. The paper shows similar abbreviations for other common method calling patterns. Although the ADO model makes it easy to use common RPC interfaces like this, it also supports much more exotic behaviors. For example, one of our composition case studies is a two-phase commit DApp where each resource manager is an ADO. It's not important to fully understand this code, but the main thing to know is that the transaction manager, or TM, communicates with the resource managers and that there is only one TM at a time. Since there's no risk of someone preempting its leadership, it's enough for the TM to call pull just once when it starts and then skip it when invoking methods later on. This is a performance win because the implementation can assume that a stable leader has already been elected and skip the first round of messages. Handling this kind of optimization would be very difficult or impossible with other models. Now that we've seen the ADO model as a high-level abstraction, I'll discuss how it relates to lower-level models. With refinement, we can prove that properties of an ADO specification carry down to a network-based specification of a particular protocol. This involves showing that for every step that the protocol can take, there is a corresponding step for the ADO. Earlier, we saw how ADO operations map onto Paxos. In reality, things are slightly more complicated because the Paxos operations are not actually atomic like the ADO. They're really made up of multiple network events which can interleave with each other. However, many of these events can commute without affecting the resulting state, so we can logically rearrange them so it's as if they happened atomically. What I've presented so far is a somewhat simplified version of Advert. This figure from the paper shows more details, including a generic template for Paxos-like protocols that allowed us to prove refinement once and then instantiate it with several variants with minimal additional effort. The table on the right shows the rough number of lines of Coq specification and proof for each component. The top rows are for the composition case studies, the middle rows are for the network refinement and safety proofs, and the bottom rows are for instantiating the generic Paxos specification. Refinement is clearly the most challenging part, but fortunately it only needs to be done once per protocol. On the other hand, this also shows that working with ADOs is much simpler, even when dealing with non-trivial composition patterns. Our code is available as an artifact on Zenodo as well if you'd like to browse it. In conclusion, I've presented the ADO model along with the Coq verification framework as a solution to the existing model's inability to handle partial failures. In terms of abstraction, it sits between state machine replication and network-based models. It gives you the flexibility to choose how to handle or ignore the partial failures that come up in distributed programming. Thanks to refinement, we have a formal link between ADO objects and their implementations, while still maintaining a clean separation between protocol and application logic. Like I said before, the paper gives a much more precise account of the ADO model, as well as several interesting case studies, so I encourage you to read that. Thank you for listening.